right, everyone, we'll go ahead and get started. We'll have folks popping in as we go, but thank you everyone for being here today and for joining us for our first Friday. My name is Amy Zimmer. I'm the Communication and Outreach Specialist for Marion Soil and Water Conservation District. I'm joined today by my colleague Chelsea Blank, our Natural Areas Conservation Planner, who will be our co-host today. We're pleased to have with us Colin Park with the U.S. Department of Agriculture and Max Ragozzino with Oregon Department of Agriculture for a summary of ongoing efforts in which tiny stingless wasps are used to control emerald ash borer. They'll be introducing us to the biocontrol agents, share how they're produced, and how they do their work in finding and controlling EAB infestations. Additionally, they will discuss how you can get involved and what this may mean for ash trees near you. Both presenters bring with them a great deal of experience. Colin is a USDA plant health safeguarding specialist in Oregon and began organizing EAB detection work in the state and overseeing pest biocontrol programs in 2007. And Max is the ODA biocontrol entomologist who has managed invasive insect biological control since 2020 and has worked on emerald ash borer biocontrol specifically since 2015. Thank you so much for joining us today, Colin and Max, and we look so greatly forward to your presentation.
Okay, well, thank you for that kind introduction. Here are some great photos of the emerald ash borer. Without further ado, we'll start the presentation. Okay, so part one I will handle for the USDA, and then Max will do part two. I'm going to go over, forgive me if this is review for a lot of you, but just to be safe, we'll go over the EAB background, the USDA program, the life cycle and damage of EAB, briefly ID and lookalikes, then what is biocontrol, USDA biocontrol program for EAB past and present, and then Max will take us through the Oregon quarantine, the slow ash mortality integrated management plan, and biocontrol agents life cycles, site selection, releases in Oregon, monitoring, and we'll have time for Q&A at the end. So EAB's native range is in temperate Asia. It was introduced in the 1990s, likely in wood pallets or raw wood of some kind. It was discovered in the Detroit area of Michigan in 2002. It's now in 37 states and 5 provinces. This timeline of spread shows that it was almost immediately discovered in neighboring states and spread rapidly. It was found in Colorado in 2013 and in Oregon in 2022. Likely it's present a few years prior to detection, which we'll talk about more later. So don't give pests a lift. EAB are excellent flyers and can be expected to move at least about 4 kilometers per year. But in the 20 years, they've moved about 40 times faster than we would expect, and that's through hitchhiking. They should be still within a couple hundred miles of Detroit, but unfortunately, they hide in firewood, nursery plants, your potted plants that you move from your patio. These can all harbor pests and disease. For EAB in particular, we think firewood probably, but then there's also raw logs, container cargo, and pallets, as I said. We now have international standards for treatment of that wood, solid wood packing material. It must be heat treated or fumigated. That's for international regulations. We also have strict requirements for plant imports. Within the U.S., quarantines and treatment requirements are harder to enforce. We have had them for EAB for 20 years, but sadly, we're just trying to slow the spread, and we continue to do that. In addition to import regulations and state and federal quarantines, public outreach and detection trapping aim to slow the spread and provide early detection, rapid response opportunities. Here you can see West Multnomah County Soil and Water Conservation District doing some trapping. So here's the current distribution map. For over 20 years, the USDA and states enforced a quarantine. That did end in 2022, but the goal of the EAB program remains the same, and Oregon still has a quarantine. To help maintain ash trees as part of the North American landscape is our goal. We continue to focus on biological control, detection surveys, public outreach, and education. And this is our USDA website for the program, which has a lot of useful information, including fact sheets and Q&A sheets about the biocontrol program. recommend checking the website out for that. Why do we care about EAB? Well, looking at the damage, here is the map of the range of native ash species in North America. You can see here it is quite extensive. It's been estimated to make up about 2% of the canopy cover of all trees in the U.S. EAB is estimated to cost tens of millions of dollars to manage and a total of $1 billion of damage each year. It also threatens about $3 billion in resources, including $25 billion of annual timber production. It has a couple of alternate hosts as well, including cultivated olive and an ornamental called white fringe tree. But the preferred host is ash trees, and there is little or no natural resistance to EAB in our North American ash tree species. Ash are vital components of many ecosystems and also a popular workhorse street tree. Wood from some kinds of ash have high value uses such as tool handles, baseball bats, basketry, hardwood furniture, and cabinetry. And of course, other uses include solid wood packing material, as we discussed, and firewood, as well as pulp and paper. There's also some significant cultural heritage for these species, especially for Native American tribes. And in Oregon, ash trees are considered important for salmon habitat. The reason for this is they are often the only forest-forming species in our heavy Willamette Valley soils close enough to streams and vernal wetlands to effectively lower water temperatures, which is important for salmon health. Now let's look at EAB. Here is the life cycle, appearance, and signs of presence. In Oregon, they are univoltine, meaning one generation per year. The larvae, also known as the grub stage, they eat the phloem, cambium, and outer sapwood in the summertime through November. The larvae and pupae, which are like the chrysalis of a butterfly stage, they overwinter in the tree. Occasionally, larvae will feed for 2 years before completing development. The galleries are the problem. They cut off nutrient flow in the tree, stressing and killing the entire tree. Attack and die-off generally starts in the canopy, which can be hard to detect. And then adults are active pretty much all summer. The problem we have with detection is that the adults don't necessarily come to the traps very readily, and also the trees start out with only a few galleries and often show no outward signs of damage at all. So detection is difficult. So here's a closer look at that annual cycle. The adults emerge in early summer from these D-shaped exit holes. And they are showy, but they're also quite small and typically high up in the canopy. Mating commences. Egg laying occurs in fissures in the bark. The eggs are quite small, about 1 millimeter in length. And the larvae bore into the tree and really enjoy that lush cambium layer. And here you have the pupa, which is at the final stage prior to the adult phase, where it will chew its way out in those D-shaped exit holes. So the larvae make these very serpentine galleries. This is a good diagnostic tool. This would be in the phloem, which is under the outer and inner layers of bark, known as the cambium. You can sometimes see into the tree that far if the bark is damaged or it's split from all their feeding, but usually you have to scrape to get to that layer and see this. And then, as mentioned, they after they pupate, they leave these uniquely shaped exit holes, D-shaped, but they are quite small. Keep in mind, it's about half the width of a pencil eraser. So EAB is an agrylus species, which is part of the buprestid family. Common names for this family include the jewel beetles, the metallic wood-boring beetles, or flathead borers. Many of these kinds of beetles are rounder in overall appearance than EAB. As you can see, EAB is kind of slender. A lot of them are showy or even much more brightly colored and metallic in appearance than EAB. But we have some really beautiful ones that are often reported. I don't know if you can see my cursor, but up on the upper right here, you've got the golden buprestid, and then on the very far right, that's the sculpted pine borer, which has really interesting appearance and Those are fun. They're actually attracted to wildfires, so you may see them if you're near a forest fire. So OSU created a forest pest detector course, which many people have taken over the past decade or more. I hear it's being renovated at the moment, but watch for that if they make it available again. So here you can see in this pop quiz that it's not always so easy to say which is EAB from its general appearance. Um, Certainly, any one of those could be mistaken for EAB pretty understandably. It's actually this one right under emerald, right under the word emerald, and then immediately to its right, this is actually a spotted oak borer, which is another significant pest closely related. But this one on the upper right, that's not EAB, but we certainly want to take a closer look at that. So here we have them next to a dime for scale, and also some other agrylus species. Then ODA put together these excellent guides, which you can find at their website. Um, I'm told they're generally impressed if they get reports for any agrylus. Most commonly, they get this one to the left of it, which is the golden bee-breasted. You can see it's a little more round shape, much more typical of other jewel beetles than the more slender EAB agrylus species. And then going by color alone tends to be extremely unreliable. Here we see many of the jewel beetles from the previous slide, but also other kinds of beetles, bees, stink bugs, even a cicada that's kind of green. So anyway, excellent resources available at the ODA website. So, okay, now we're going to talk about control strategies. And to start with, we need to reiterate that detection is very difficult and early detection is rare. Following initial detection, we usually already have about 5 years of infestation. And communities typically experience an exponential rate of loss at that point, which reaches 100% in less than 10 more years. Now, we're going to talk about mitigation strategies that have been developed to hopefully slow that. But this is what a lot of the Midwest experienced over the past 2 decades. So here we see the range of control methods we've been using for EAB nationwide, which have been refined over the years and will also be used in Oregon. It has been shown that these are not sufficient on their own. For example, one of the most aggressive efforts to control EAB was done in 2004 in Canada. The government there removed 150,000 ash trees in southwestern Oregon to create a sort of fire break, but it was detected almost immediately on the far side. Now, it's not clear if they were already there or if this just wasn't effective, but you can see it's very difficult to figure out how to get in front of this, even with very extensive measures. So here in the western U.S., we also have the Rocky Mountains, which was a much larger break, but even in that case, quarantines just weren't as effective as we would wish. So we have to add to these methods something called biocontrol, biological control, aka biocontrol. All the previous methods can be helpful components of an integrated pest management strategy. IPM, or Integrated Pest Management, uses a system-wide approach to a particular pest control situation, and it favors holistically beneficial solutions. So often, if at all possible, IPM integrates biocontrol into that. And there are 2 kinds we typically talk about. Conservation biocontrol works with natural enemies already present or likely nearby, typically natives, but not always. And in contrast, classical biocontrol looks to the native range of the pest itself for safe options that could be added to our ecosystem. Insects are ideal for this job since they are incredibly diverse and often very host specific. So here you see an example of tansy ragwort, originally from Europe, and then a subsequent introduction of the tansy ragwort flea beetle, which has been used to effectively control that pest, exotic pest. So this is called classical in part because it's been around a long time, and more importantly, it kind of coined the term in the literature for biocontrol. The reality is, of course, that conservation biocontrol is much older, but it often goes unnoticed. Um, so anyway, with classical biocontrol, one of the first documented cases of this idea working well was the cottony cushion scale, which threatened the brand new citrus industry in California in the late 19th century. A brave entomologist was dispatched to the scale pest native range in Australia, and they found a darn effective and cute little predatory beetle. They released 35 of them and redistributed them throughout California and had almost immediately successful control. So that was way back, a very early example, and something like that gets people's attention. It's also been embraced by Oregonians for at least over 80 years now, even as we've become more concerned about non-target effects and increased the regulation for that. In Oregon, we've been successful with we've also done successful control of insect pests in Oregon, including brown marmorated stink bug, spotted winged Drosophila, and cereal leaf beetle, which Max can tell you guys more about if you have questions on those. So I'll just briefly go through this. Basically, we started in 1943 with St. John's wort leaf beetle, but it's also been proven successful with tansy ragwort, diffuse knapweed, Dalmatian toadflax, purple loosestrife, and leafy spurge. Those have been greatly reduced as a result of agents released. In total, we've done about one per year, total of 80 on 30 different noxious weed species. In order to be released, they need to be tested to be safe for non-targets prior to receiving an APHIS permit, and also as part of that, they must be approved by a what's called the Technical Advisory Group, which is an interagency group of experts who look at all the scientific evidence and either request more research or move it on to the next stage, which is then tribal and U.S. Fish and Wildlife Service consultation and environmental assessments. Anyway, as a direct harmful impacts for the Oregon noxious weed program are estimated to be worth at least $17 million per year, and they also show a really high cost to benefit ratio. So why add biocontrol to an IPM strategy? Well, for classical biocontrol, it must be a non-native pest with few endemic natural enemies. It must be well established and widespread, causing significant damage, which provides the incentive for control. If eradication is not possible, and also adequate control is not even possible or too expensive to be practical, that makes a good candidate for biocontrol research. And here on the right, we have a graph of pest density or quantity over time, which following the introduction of a biocontrol agent resettles at a lower equilibrium. The population continues to fluctuate and may still cause some problems, but it is hopefully at a more acceptable level. The goal is never eradication for a pest through biocontrol. In very successful instances, we can see dramatic reductions in range and density, such as with those weeds I mentioned. However, this can take many decades to occur, and this is a challenge for EAB especially since, as we saw, mortality can be expected sooner than that. So it's part of our strategy. It's not a silver bullet. And then so briefly, I'm wrapping things up. This is a history of the biocontrol program. It started out with a survey for endemic biocontrol agents. These would be generalists attacking agrellus species in Michigan. And 3 species of wasps and 3 families of common parasitoids were found to be general enough to try nibbling on some EAB, but less than 1% control was found, and so that's far from adequate. We had much better luck in EAB's native range. 4 promising species of parasitic wasp were found in northeast China and began to be studied. This was around 2007. USDA continues to work with all of these, though only 3 are suited for Oregon's cooler climate, which Max will share with you. These are our biocontrol agents. You have one that's a singleton that just lays one egg in an egg of EAB, and while the others target the larva and will lay multiple eggs. attacking each larva. Nowadays, there are many excellent methods for testing host specificity. Um, in this case, we were looking at a lot of non-target jewel beetles, including native jewel beetles. And this is an example in these photos here of how that's done. These would be no-choice tests, as shown in the photos. And with those, for um, a gravid female parasitoid is given a species of larva to use as a host, and no alternative. So it has to use that or die trying. If that relatively simple test shows signs of being inconclusive, there are also lab methods that try to stimulate more real-world conditions. Okay, so here's an example of some of those more complicated setups. This is olfactory and visual tests, which give the specimen a choice of essential oils and possibly basic color signals, and they choose one tube or the other. And so the long and the short of it is that these two agents had the most complicated results, but ultimately these tests combined with tests outside the lab in China showed that these were safe to release, and they went through the entire National Environmental Policy Act in that process before they were permitted. And okay, so this is pretty exciting. This is some photo collages from the EAB biocontrol rearing facility, which are my last slides before I hand it over to Max. So a lot of photos here, but just trying to show the fun and also complexity of doing this work. So raising parasitoids requires rearing EAB and a steady supply of ash logs, bolts, and leaves. So here on the lower left is a network of sources for those leaves. And up in the upper right, we have the dedicated staff at the facility. On the lower right are examples of the logistics involved in procuring and maintaining a supply of ash logs for growing the EAB to use as hosts. And then in the middle are those chambers that they use to grow the EAB and collect them for further use. So quite the operation. The goal is to produce eggs. A steady supply of EAB eggs are crucial to the whole operation. So under lab conditions, they oviposit onto the sterile medium, which you see here with the pen pointed at it. Excuse me. And then EAB eggs are used for either research, egg parasitoid rearing, or placed on fresh ash bolts and allowed to develop into EAB. On the left here, we see ash bolts having their cut ends waxed to help keep them fresh for the duration of that rearing. They are subsequently exposed to the larval parasitoids who use them to reproduce. After those insects complete their development in the EAB host, they must be collected and quickly distributed to cooperators for release at their sites. Okay, and so distribution is also coordinated with this group, and they use the Map Biocontrol app to send to coordinators both or ranging from state, university, federal, municipal, tribal, and other. And in Oregon, all our releases are organized by ODA and specifically Max. It's been a very successful program. Here's the stats and roughly where they've been sent as of 2023, which is the latest map I had available. But we've got over 8 million parasitoids sent to about 1,000 release sites in about 30% of EAB infested counties. So a huge effort. In 2024 alone, they provided parasitoids to 166 sites, including some in Canada, and 29 of those were brand new counties. And in total, they covered 138 counties in 24 states. So quite the logistical operation, and I also want to thank them for providing most of the slides that I shared with you today. So I will now hand it over to Max for part 2.
So thank you so much for that introduction. Wonderful background about the federal work. So to start things off, I am Max Ragozzino. I come from the Oregon Department of Agriculture, and we are a regulatory agency, so I will start with a little bit of regulation. The state of Oregon does now have a quarantine in place. It restricts movement of ash, olive, and white fringe tree wood from the infested counties of Washington, Multnomah, Yamhill, Marion and Clackamas counties. Essentially, you cannot move woody material over that border. This includes nursery stock, cut wood, firewood. You can move them within the quarantine, but we advise restricting movement as much as possible to prevent movement of EAB to uninfested portions of the county. But if you do have a business need or a need to move wood out of the county, reach out to us. There are ways to do it safely, and we just want to make sure that if you are moving wood, that it's being done safely so that EAB is not spreading with it. As Colin mentioned, we use an integrated pest management strategy to address EAB in Oregon because eradication is nearly impossible. If the Canadians weren't able to do it by felling over 100,000 trees with about a 1 mile buffer between where they knew EAB was, it wasn't going to happen. Eradicating invasive insects is difficult at the best of times, and EAB is maybe one of the worst candidates. So we use what's called SLAM, or slow ash mortality, to slow the spread and mitigate populations. In order to do a SLAM program, we have to use some of the characteristics that the beetle uses against itself. So EAB are attracted to stressed ash trees. In their native range, they're a decomposer. They like to hit a tree that's on its way out. Maybe it's been damaged by another insect, or it's been, stressed by wind or ice damage. And it is kind of one of the things that takes a tree out and allows new healthy growth in the forest. So we can utilize that and stress out some trees on purpose. We girdle some ash trees by removing a 12-inch tall strip of bark all the way around the trunk. And these girdled trees are extremely attractive to EAB. So as EAB are flying looking for their next spot, they'll land on these trees preferentially. So you can see in this bottom picture, on the right is a tree that was girdled, and on the left is one that was not. So you can see that canopy is thinning, those leaves are browning. The tree looks unhealthy because it is. We then felled those trees in the fall, and any of the eggs or larvae there were destroyed and removed from the field. Simultaneously, we treated trees with a systemic insecticide, emamectin benzoate. These are trunk injections, so there's very little non-target impact. It goes straight into the tree xylem, which moves water up to the canopy. So that allows the chemical to be distributed right where EAB adults are feeding and right where larvae will be feeding. It lasts for 2 to 3 years, and we only chose healthy, preferably female seed-producing trees, so that when after EAB moves through, there will be some seed-producing trees left to help rebuild the seed bank. Thankfully, due to a bit of a quirk of the parasitoids that I'll talk about in a minute, the biocontrols are not impacted at all by our chemical treatments. As Colin mentioned, we utilize a couple different species of parasitoids. These are stingless wasps, as in they cannot harm people or pets. You can see on this picture of Spatheus galeni right here, where a honeybee would have a stinger, it has an ovipositor, this really long, slender extension of its abdomen. At the end of its abdomen, it uses to lay its eggs. So, as Colin mentioned, these are extensively tested for non-target impacts. These parasitoids are different than parasites in a very specific way that is helpful for us in EAB. In terms of humans, a parasite is a tick. It's annoying, it's a bloodsucker, but when you remove it, you're still alive. In humans, a parasitoid is the chest burster from Alien. When it's done, you're not surviving that. These parasitoids will actually drum their antennae on the outside of the bark, feeling or listening, depending on how you want to anthropomorphize it, for the beetle larva chewing under the bark. They'll then use this long stinger, or this long ovipositor, to drill into the bark, lay their egg on the larva, which then hatches and eats the larva alive from the inside out. So as Colin mentioned, we're using 3 species of biocontrol agent here in Oregon. We're using Owobius agrilli, Spatheus gallini, and Tetrascus planopenesi. Spatheus agrilli, the fourth species that Colin mentioned, is from a little bit further south in China, around the area of Beijing, and it's more climatically matched to places like Louisiana and Georgia than it is for Oregon. When EAB are attacked by a parasitoid, it stops their development. So Oobius lays its eggs inside of the EAB's egg, on the outside of the bark. It then hatches and stops EAB from ever hatching or developing as a larva and doing any of that damage that Colin mentioned about feeding on the phloem and the inner bark of the tree. Oobius are really tiny. You can see them on a dime there, and they end up turning the eggs pitch black. Tetrascus planopenesi is a little bit larger, but it's still one of our smaller parasitoid wasps. Because it's a little bit on the smaller side, it has to utilize smaller ash trees. This is still perfectly viable, but it does mean that some of our larger trees can be unprotected by Tetrascus. So Tetrascus will find a larva, typically larger, later instar larvae, and they'll prevent it from ever becoming an adult. So you can see it drilling into the bark here. And Tetrascus is highly gregarious. It can have up to 60 offspring per an individual EAB. So what it doesn't have in size, it makes up for in numbers. And Spatheus gallini is slightly less gregarious than that, but it is a little bit larger, so it can attack EAB in nearly all size ash trees. It lays its egg similarly in larger larvae and has between 6 to a dozen offspring per EAB larva. Just to go over that with visuals, the parasitoid drills into the bark, finds a larva, lays an egg that's almost too small to see with the naked eye. That egg hatches, and instead of there being one healthy EAB, you can see all of these little, looks like maggots, eating the larva. Those develop, spin their own cocoons, and those will eventually turn into tiny, further adult wasps that will then emerge from the tree, chew their way out, and find more EAB larvae to attack. We've been doing this in Oregon since 2023, the year after we discovered EAB. And when we look for a site that we want to release agents at, that we think these parasitoids will be successful at, we're looking for a couple of characteristics that you all can keep in mind as, you know, for the future. We're looking for large stands of ash with mixed age classes. So we're looking for a site where all three of our species can establish and be successful. We're looking for low levels of EAB. We're looking for a site that has EAB detected, but we haven't seen mass mortality yet, because we're also looking for those trees where they'll be around for a couple of years. Sites where EAB has already burned through and eaten all of the trees, that's not going to be very useful for the agents, and they're going to have to disperse quickly. And finally, an understanding that this is a long-term process. It requires at least 4 years of cooperation for 2 years of releases and 2 years of subsequent monitoring, but with an understanding that this is something that will hopefully save ash regrowth and ash as a species in Oregon. It likely won't save the standing ash trees. All of that is a little bit theoretical, but how do we actually get the wasps in the field? You saw in Colin's presentation at the end about how they were producing those bolts and waxing those and exposing them to parasitoids. For Tetrascus and Spatheus, they'll actually ship us those bolts. So they ship us these bolts that we hang in the field, and as the weather permits, as the weather warms up, and those parasitoids hit the right life stage, they'll emerge out, and hopefully that synchronizes them up with the EAB in the field. We'll also release live adults when the time is right and the rearing facility has them. And then finally, we'll also release Oobius, the egg parasitoid, in what the rearing facility calls oobinators, which are a little pill bottle stuffed with that EAB eggs on paper media with a coarse mesh on the bottom so that Oobius can emerge out. So far to date, we've been releasing on in Oregon right now in 4 counties. We've been releasing on private and public lands. These sites have been monitored annually so far, and as Colin mentioned, new counties are a priority for both USDA and ODA. So Washington County has gotten a little bit of love. Clackamas and Marion County have gotten just a little bit so far. But new counties are a priority. So as EAB spreads and into Marion County deeper, we are always looking for new sites. To date, we've released 7,300 Oobius, a little over 6,000 Spathius, and 13,000 Tetrasticus. To let you know how it's going so far, it's going pretty well. So far, monitoring is ongoing. Felling the trees that in at the release sites and debarking them is the gold standard, which you can see on the right here, where you can see actually Tetrasticus pupae and larvae in there, instead of where an EAB would be, curved over like that. Trapping using yellow pan traps is another way that we can detect parasitoids, but it is a little bit hit or miss. You don't know if you've missed them or if the traps are truly negative. But we're also always trying novel methods. We're developing new methods with USDA and other researchers every year. And every year we try new and better methods and get better at detecting them. And to date, we've already recovered Tetrasticus and Spathius at one of our previous release sites. I do also have to give a massive shout out to everyone. Cannot believe I forgot to put Marion SWCD on here. All of our local and federal cooperators are what makes this happen. All of you all in the room today are how we do a project like this. Area-wide projects and statewide management is hard at the best of times, and working with folks like you all make it so much easier. And with that, I'll take any questions.
Let's see. There's a question about, are there any Oregon-specific ecosystem or wildlife impacts that have been observed in response to any of the EAB IPM interventions, like biocontrol? Any differences or lessons learned compared to other states?
Yeah, there are definitely. So right now in around the Pudding River Butte Creek infestation, um, we've seen a lot of impacts from EAB infestation there. We think that infestation is a lot older than the Forest Grove area infestation based on how far in decline those trees are. And at that site, that is what a site with that's what sites with almost no intervention look like. Stands are basically 100% dead over 5-10 years time span where there are just no ash standing. Um, Comparing that to Forest Grove, where we detected the infestation a lot earlier and got boots on the ground, biocontrols released, and have been performing these did some slam activities in 2023 and 2024. We're seeing a lot slower decline. Hopefully that continues into the future. But we've also seen recently in some academic work from the East Coast that functionally the more parasitoids released at a site, the longer the ash survive. So um, we are hopeful that we can continue to release as many wasps as the USDA facility can send us. But these parasitoids will also reproduce in the field and hopefully multiply quickly. And yeah, and the differences in lessons learned compared to other states is that's how we decided to do this SLAM program. We are very fortunate right now because we're the, I believe, 27th state with EAB infestations. So we've had a lot of hard lessons, and a lot of the methods that we described and techniques and decisions that we made were guided by conversations with folks at the Forest Service, USDA, APHIS, and ARS, to make sure that we were doing things that were not just going to be the best practices for the state as a whole, but also the most cost effective and have the biggest impact possible.
Let's see. Another question asking, how do you know if the bolts contain some EAB that haven't been parasitized?
That's a great question. So we actually don't, but there's a fun little trick that we can do here. Because emerald ash borer have a minimum 1 year life cycle, we can put the bolts out in the summer and take them down in the fall, and then that resolves the issue. If any beetles would have emerged, then they would have emerged, the following spring. and that really kind of seals it. But simultaneously, also, we're putting these out at sites where we've confirmed there's EAB present, and one or two beetles getting out of a bolt, worst case scenario, is a drop in the bucket when each tree that's infested with emerald ash borer can have easily hundreds of beetles emerging out of it.
See, there's another question. Could you please re-describe what we were seeing in the photo of the gold standard for debarked trees?
Yeah, so that was Tetrasticus. I can pull up the picture again. Right here, you can see basically this hollowed out section where you can see all of the black pupae and white larvae of Tetrasticus. You can picture an EAB larva taking up this space. Instead of there being one larva there, you can see these dozens of white grubs. Those are at the last instar, the last stage of larva, and these black pupae that are Tetrasticus getting ready to pupate or, metamorphize the same way a butterfly turns into a chrysalis. And that's what we're seeing there. So this is actually those Tetrasticus getting ready to emerge out. So if we hadn't debarked this tree, that would be a bunch more Tetrasticus to emerge out. And when we see this, we'll actually put them in a vial and hopefully they continue their life cycle.
The type of reported metrics ODA and USDA expect to report out on after the 4 years of data is gathered?
Yeah, so it depends on which method we're using for monitoring. If we're felling and debarking, that gives us that gold standard data because we can see how many EAB larvae are present at a site, and then how many of them are parasitized. So we can actually report out a direct amount of this percentage of the beetles have been controlled by parasitoids. If we're using things like yellow pan trapping, then we can report how many parasitoids we collected per trap, which gives us a little bit less specific, but still a presence or absence metric.
Okay, and moving right along, the questions keep coming. This is great. Let's see. Are sites suitable for parasitoids if the EAB has not been detected on the site? And how far will the parasitoids travel?
Typically, no. There are very few exceptions to that. If EAB are detected, respect what a property boundary is. So if we've detected EAB, say, in a street tree right next to a natural stand, in that case, we might put forward that natural stand as a potential biocontrol site with the understanding that EAB infestations are cryptic and they're hard to detect, and we had a known positive feet away from it. But typically, no. Typically, a site needs to have confirmed EAB presence at the site in order to release because the parasitoids need EAB to reproduce in. So unless we're pretty confident that there's going to be EAB there, we won't release. They'll travel pretty darn far. Awobius is our shortest disperser. It doesn't travel nearly as far as the other two, but it'll still travel. Awobius is the one that's a couple, like around 1.5 to 2 millimeters long. So it won't travel very far, but it can still travel hundreds of yards a year. Whereas Spathius is our best flyer, which can travel up to 14 miles a year. They actually detected it in New England at their control sites. They thought they put them 14 miles away. They thought that was far enough from their release site, and they picked them up within a year. They can travel pretty closely to the maximum range that EAB can spread.
So this is a good question. Can you speak to any other unintended impacts that could result from the mission to slow down the EAB problem?
Yeah, I guess unintended impacts is always something that we're very cautious of. With any sort of large program like this, there's a lot of things where there will be impacts. Like removing trees is obviously very impactful to the communities it happens in. Like, um, for instance, in Forest Grove along 13th place, in I think 13th Ave, sorry, we detected those trees were really far gone. So chemical treatment was not going to be an option. These trees had maybe 2, 3, 4 years of life left. And with between ODA and ODF, we worked with we got those trees removed at no cost to the homeowners, but that still makes a big impact to the community. when suddenly your urban canopy, your street trees are all gone. So that's going to be a massive impact for a lot of people. And we try to mitigate that by working with folks like Friends of Trees to plant replacement trees and things, but that's not always possible. And, you know, some of the missions to slow down the spread of EAB include things like, you know, like we advise insecticide treatment to be used for trunk injection, but there are also options for soil drench or basal bark sprays, which have further non-target impacts for some of our native species.
So the next question is, could biocontrol being studied have the potential to take over the role emamectin benzoate in riparian areas?
Yeah, I don't think so, unfortunately. As Colin talked about with that economic injury level, we're never going to eradicate emerald ash borer, and emamectin benzoate can do that. When you treat a tree with emamectin benzoate, it functionally removes it from any sort of EAB damage. The parasitoids won't be able to do that. The parasitoids, we hope, will knock EAB down to the point where we're talking about EAB as another forest pest that has bad years and good years. But right now, it's not likely to be something where we can, use it to purely protect those trees forever. We hope that it'll pick up and hopefully it can, have more of an impact over time as we're able to release more. But yeah, I don't think it's ever going to replace insecticide directly.
Do you release various combos of the 3 biocontrol species?
Yeah, we release all three at every site in Oregon because those we've actually studied them pretty extensively, competition between them and like resource allocation and things like that, and they actually work very well together. So we'll actually selectively put like the Oobius on the larger trees that have a lot more likelihood to have EAB eggs, and we'll put the Spathius in the similar areas with those big trees with lots of larvae. And then the Tetrassicus we'll put on the smaller trees where they're slightly lower. But then I just talked about how Spathius can fly 14 miles. So at the end of the day, they will find their own place within the site one way or the other.
Wonderful. Well, I think that concludes the remainder of the questions in the chat. Thank you so much, Chelsea, for getting those out there. Yeah, I definitely second Chelsea. We thank you so much for your time and your knowledge and your expertise and sharing that with us today. So folks are aware, this is part of a EAB series that we have at Marion Soil and Water Conservation District. So keep an eye on our events page for upcoming events in this series, as well as our future upcoming First Friday presentations. Our next event in this series is posted on the screen here. We'll be having an emerald ash borer trapping workshop in which community members can learn how to trap EAB and take home a trap for their own properties. So again, please stay tuned on our events page for more for this and other topics. And we so greatly thank you both for joining us today.